let's see how extend the abstract machine E with a fixed point construct. So abstract machine E with fixed point construct. So this is the reduction rule for fixed point construct. Fix x a dot e reduced to fixed point construct itself, substituted for variable x in expression e. So we have this reduction rule for fixed point construct. Then let's try to extend the state transition rule for abstract machine E with a new case. Suppose that we are currently analyzing, so it's a right triangle, this fixed point construct. Under environment eta, then we should keep analyzing this expression E. So we analyze expression E, and then what is the new environment? We have to carry everything in this environment eta, and inside the expression E, this variable x is counted as a free variable. So we have to add new mapping for this free variable x. And the value for this free variable x is, of course, this one. So you just copy fix xa dot e. So this is fine, except that there is a problem with this mapping. The problem is an environment contains mappings from variables to values. So the right side of this whole right arrow should be value, but this fixed point construct is not a value in general. So we can't use this mapping for the simple reason that this fixed point construct is not a value. Whereas environment consists of mappings of this form, variables mapped to values. But this is not a value, so we can't use this reduction, this state transition rule. So the solution that we use to deal with this fixed point construct is, instead of allowing this general form of fixed point construct, we allow a particular form of a fixed point construct that can be counted as value. So usually we use this fixed point construct to define a recursive function. So the plan now is we'd like to identify a subclass of this fixed point construct that is that represents recursive function, so they can be counted as value. So what that means is that we are going to extend the syntax for expressions with this function recursive function construct fun f x a dot e. So this is we regard this new form of expression as value. So this is a value, and it is going to denote a recursive function f. So recursive function f with the formal argument x. This is argument, and this is argument type, and it's a function body. It's a function body. So the plan is we introduce a new form of expression which is counted as value, and this construct is going to denote the recursive function. And it turns out that this is a subclass of this fixed point construct because we can define this function construct in terms of fixed point construct. So it is actually fixed point of a function f of type a arrow b, and the expression is lambda x a dot e for some appropriate type b. So in other words, we can think of this fixed point construct as a shorthand for this fixed point construct. So this function construct is a shorthand for this fixed point construct. And we are going to regard this function construct as a value. So that's the plan. Let's think about the typing rule for this function construct. So the question is, how do we determine under this typing context gamma, how do we decide the type of this function construct? So we intended to use this function construct to denote recursive function whose formal argument is x of type A. So it is going to have some function type of this form for some appropriate type here. And how do we decide this type, the return type? So to find out the return type or the type of this expression E, we have to think recursively. So we are going to find out the type of expression E, and we have to make a guess on its type. So let's say we make an educated guess on the type of this expression E and say it is B. So we think its type is going to be B. Then when we type the expression E, function f is going to have type a arrow b. We are not sure yet if b is indeed the correct type for the expression E, but it's just a guess. So let's assume that the return type is B. So the type of this expression is B, and then the type of this function f is going to be a arrow b, and x is the type A. So from the point of view of this expression E, both f and x are free variables. So you have to provide these type bindings. And if you can construct the derivation tree for this typing judgment, that implies that your guess was correct. Your guess was the return type is B. And if you can construct the typing derivation here, then your guess was correct. So the return type is actually B. So you'd have return type B. So the point is, when you think about the typing rule for this function construct that denotes the recursive function, then you have to also think recursively. So this is the typing rule for this function construct. Now let's extend the state transition rule for abstract machine E with this function construct. So first, let's say we are currently analyzing this function construct fun f x a dot e under this environment eta. So we can think of this one as a particular form of a function. It's going to denote recursive function, which is a special case of a function. So what we do is, this is the value, and it's something like a function. It's something like a lambda abstraction. So we build a closure and return this closure as a return value. So we return some new value here, because we use this environment, we have to build a closure. So we build this closure, and the environment is this one, eta, and the function is this recursive function. So in this way, we build a closure for this recursive function. And the second case is similar to the rule for ordinary lambda abstraction. Suppose that we are currently returning, so we have this one, E2. Suppose that we are currently returning this closure for this recursive function. Let's say this is eta prime. Then it's simple. So it's the same as the case for closure for lambda abstraction. So we are going to keep analyzing this expression E2. So we are going to have this hole here for expression E2. And here we fill this, we use this closure. So we remember this closure eta prime fun fxa.e hole, and then we keep evaluating, we keep analyzing expression E2 under the environment obtained from this annotation. So there is actually nothing new in this rule if we regard this one as a special case of function, lambda abstraction. Finally, what happens if everything goes okay and we have this sigma eta prime function fxa.e, and we are returning value v, which was perhaps obtained from the argument expression E2. So it's time to perform function call. So we have this closure or function with its environment, and we have its an argument. So it's time to perform substitution, or we are going to extend the environment and analyze, evaluate this expression E. So at the next step, we are going to analyze or evaluate the body of this function, which is expression E. And the remaining question is, what is the environment for this expression E? So first, we have to restore this environment eta prime, which contains the values for all those free variables in expression E. So just like the case for ordinary lambda abstraction, we restore this eta prime. Eta prime goes here. And next, from the point of view of this expression E, both variables f and x are also free variables. So you have to provide the two entries in this environment. The first for this variable x, and the second for this free variable f. So what is this? The value for variable x, the value for variable f. So of course, the value for variable x is the one here. So it's basically the argument to be supplied to this recursive function. So x is mapped to value v. Then the remaining question is, what is the mapping for this function f? So inside this expression E, the function f, this variable f, points to the recursive function itself. So we have to have something that would correspond to recursive function f itself. And that is precisely the closure for this recursive function. So what we do is we actually copy the entire closure over here. So this is going to be eta prime fun fxa.e. So essentially what we do is we take the pair, this environment and this function construct, and interpret it as the recursive function f. So every time you pass a recursive function, you have to pass not just this function construct, but also this environment, because combined together, we can properly build a recursive function. So that's the way that we extended the abstract machine E. This is the new state transition rules for abstract machine E in the presence of this function construct. And this function construct is basically a special form of this fixed point construct. And so this is a particular form of this fixed point construct, and it is designed to denote, it is designed to build a recursive function f, whose formal argument is x, and function body is e. So now we have extended the abstract machine E with recursive functions.